Welcome back. So this is lecture 39 in this course. We were discussing Hamiltonian Monte Carlo, and I briefly talked about the BRMS package in R. Okay? So there is a library in R. You can install it and look at the description of the function. So the library is called BRMS. Okay, so the library actually implements a Hamiltonian Monte Carlo sampler in the background and gives you posterior distributions and basically also trace plots and everything you need basically, right? So basically it implements a HMC sampler for you and it gives you posterior distributions for your parameters. Okay? So we will be going forward in this course, we will be using this BRMS package, right? The topic for this lecture, lecture 39, is I will briefly discuss the syntax of BRMS and how do we use it, right? So, thing is that the package will not ask you any important information about the sampler. So, you do not need to worry about implementation of the sampler. Only thing you need to worry about is your likelihood assumption and your prior assumption. So, if you can define your likelihood assumption and prior assumptions properly, it will do the job for you. Okay. But let me briefly explain what is this package and what it does in the background and all that, right? So, um, so the library we are talking about is called BRMS. So if you do not have it in your system, you can install it. You can take a look at its documentation, right? So you will find it. The library is also available for Python as well. So I think PyBRMS or something. So you can use it in R, Python, or anything you want, right? Actually, the main thing is not this library. There is another interface that works behind this library. So whenever you call this library and whenever you want to implement your model using this BRM function, which is what calls an HMC sampler and implements it for you. Whenever you apply this BRM function, it actually writes a piece of code in a probabilistic programming language called STAN. Okay, so the name of the language is STAN. So what BRM function does, that it writes code in a specific syntax in a programming language called STAN, right? And this programming language has been specifically developed to implement this HMC sampler. Okay, so that's why you can explore this site, which is called MCSTAN, I think. So this site contains all the information about this STAN development program, right? So there is a whole program, not a software program, but there is a whole sort of research program which looks into it, which develops these algorithms, these samplers for Bayesian inference, right? And the underlying algorithm behind all this is HMC, right? And they also developed a lot of interface and functions and all that to make this job easier for us, right? So this is very handy when it comes to implementing complex models. In fact, although this is not what we are going to do in this particular course, this course is supposed to be just introduction to Bayesian modeling, but when you study advanced Bayesian modeling, you will be frequently using this package, STAN package, to implement complex cognitive model. Okay, so for example, you can implement some race models, okay, accumulator models, right? Or let's say some memory models directly into this package. For example, multinomial processing trees, mixture models, right? So you can implement those in STAN, right? BRMS is basically an R interface or Python interface for us. So the purpose of BRMS is to make the job easier for the users who have previously used some other linear modeling platforms, like for example LME4. So if someone has used LM4, they will find it very easy to BRMS because it has similar syntax and everything. So that's why this package was developed. But the actual thing in background that is running the business is this STAN programming, right? So once you learn STAN, you will be able to do a lot of things. You can implement any complex cognitive model, right? Because it allows you a lot of flexibility. In BRMS, you can only do linear regression modeling. So basically, the regression models that we will talk about later in this course, and also hierarchical regression models, those all you can fit in BRMS. Okay? But for other purposes, STAN would be useful. For the purpose of this course, we are not going to go into STAN, but we will stick to BRMS because that's all we need for this course. Okay? But remember, always this BRMS function would implement some STAN program in the background. Okay? So let me just briefly show how a STAN program looks like corresponding to, let's say you write a whenever you write a BRMS code. Okay? So the idea is this. So let's say you have this model, you want to implement this model with likelihood assumption. Let's say your model has this likelihood assumption that reaction time in ith trial comes from a log normal distribution with parameters mu and sigma. Let's say this is your likelihood assumption and these are your prior assumptions. On mu, the prior is normal 6, 1. On sigma, the prior is truncated normal 0, 0. Let's say 5. Let's say these are the priors on mu and sigma. Okay, this is likelihood is log normal. Okay, RTI is some reaction time, and let's say you have your data says that your data gives you, let's say 500 data points, RT1, RT2, RT500. So you have 500 data points here. Okay, so this is so you want to model these reaction times using this log normal likelihood and these prior assumptions. Okay, so how do we do this? So in BRMS, you just need to use, it's straightforward, you just use this BRM function. Okay, then you write the outcome variable here. What is your outcome variable? Reaction time. Okay, and we write that reaction time come from this 1 indicates actually intercept. You will understand it later on when we do regression modeling, but you can ignore this for now. This syntax is actually not very intuitive, but we'll go ahead with this. So you write it like this. So RT is the outcome variable and it comes from some distribution. You can think about it like that. Then you write the data here. So it will take some data in the form in a form of a data frame, and this data frame should contain this variable RT. Okay. So once you have passed the data frame, then you need to define the likelihood assumption. So basically family, which describes the distribution that you want to use to model this outcome variable. So what distribution you are assuming that is generating these reaction times? You're assuming log normal distribution. So basically family defines your likelihood assumption. Okay, fine. So you have defined the likelihood assumption so far. Now you need to define your priors. So prior equals to concatenate prior. Okay, so the first prior. So first prior that we want to define on is on mu, second is on sigma. Okay, so here you can write the prior that you want to define on mu. So what is the prior on mu? Normal 6, 1. So you'll write it like this, normal with a small n. So this is basically a already well defined distribution in BRMS package or STAN package, right? So that's why you have to write it in the same format. You do not need to write it inside inside those quotes, but you can write just directly like this. So normal 6 1, okay, and then you need to define the class here. Okay, so let me start actually slightly here, otherwise it will become difficult to write. Prior equals to C. Prior, first prior is normal 6 1, and class of this prior is intercept. Okay, so this actually will understand when you start regression modeling, but idea is that we are defining this prior for the parameter mu. Okay, now we define prior for the second parameter that we have, prior normal. What was the prior? 0, 0.5, class equals to sigma. Okay, and once you define class as sigma, the algorithm in the background will automatically so there is some program in the background which transforms this into a Stan code, will automatically understand that this can't be normal 0, 0.5, this has to be truncated normal 0, 0.5, because sigma can't be less than 0. Okay, all right, so this is how we define likelihood and prior. Okay, so this is, so most of the work is done here. Now you can, if you want, you can define number of chains equals to 4, number of iteration equals to whatever, 4000, 2000, how many iterations you want in each chain. Then define number of warm up, 1000 or less or whatever, number of cores equals to 4. Okay, these three things are by default values, so if you do not need, if you do not even define them, you will still get these many iterations per chain. Okay. This you can leave out if your computer does not have 4 chains, four processing cores, right? I think most of your computer has it, so you can go ahead with this. So this is how, so this is the BRMS code to implement this model. Okay, so when you run this code, of course you should store it somewhere, let's say M1 or whatever, MFit. No? So when you run this, so this object M1 would store after the so it will show some messages that sampling is starting, sampling is done, and when sampling is done, M1 will store your posterior distributions and other things, right? So if you retrieve a summary of M1, it will show you everything, basically 95% credible interval and all those things, and whether how good was model fit and all that, right? It would also show you something called ESS and R hat. ESS is actually effective sample size. Okay, what does it mean? It means that how many uncorrelated samples effectively you are getting, right? So do you remember the situation when your step size was too low? So when step size is low, then chains get stuck, right? And you get a huge number of correlated samples. Your rejection rate is very low, you get a lot of correlated samples, basically you end up accepting everything. You get huge number of correlated samples, the chains get stuck in one place, so they keep going in one direction. So those are cases of correlated samples. So in this case, the effective sample size would be very low. So when, for example, the step size is low. So this can happen in cases where chains are getting stuck, so model is not able to perform properly, right? So ESS is a good metric to ensure that model has converged properly. Okay, so it is a diagnostic. So both R8 and ESS are actually diagnostic. So you want that ESS is at least, let's say, greater than 400 or so. If it is less than 400, then you are in dangerous territory, because you tried to collect 4000 samples, and out of 4000 samples, if even 400 samples are not effective, then you are in dangerous territory. So we want at least 500 or more samples at least to get a reasonable approximation of the posterior distribution. If you have such few samples, then you might get not a very good posterior recovery. Okay. R hat is a measure of chain mixing. So it tells you how well chains are mixing into each other. So I think it measures the variance within chain divided by variance across chains. So basically ratio of variance within chains and across chains, right? So if R hat is too large, right, I think it's the other way around. It's variance across chains divided by variance within chain. So if R hat is too large, so let's say R hat is, so usually it will be around 1. So if everything is good, it will be around 1. But if R hat is too large, by too large I mean if it's, let's say, greater than 1.1, even that is a large value. So if it is, let's say, greater than 1.1, then it could be the case that chains are not mixing well. Okay. So these are diagnostics that you can take a look at to ensure your model is converged, right? Rest you will get posterior and everything. You can use some functions to get the posterior samples, to extract posterior samples. So I think the function is just posterior samples and then M1, something like this, right? So this keeps changing. So maybe it is extract, right? So that you can figure out. So what is the function you use to extract posterior samples, right? So this is the basic idea of BRMS. Okay. Now, but what BRMS is doing in the background, it is implementing this model into a STAN. Okay, so it is writing this model on a STAN interface. How does it write on a STAN interface? So this is how a STAN interface looks like. Okay. So it creates a .stan file or a STAN program where you need to define these things. So basically, first thing you need to define is the first block contains your data. Okay, so first you need to define data. Okay, so in data block, basically, of course, it similar to Java, you will need to define properly what is your variable type. So for example, vector of length n rt. So there is an outcome variable rt which is of length n, then integer with lower equals to 0 n. Okay, so n is the basically number of observations, right? Or you can call it n obs or something, n obs, right? Okay, so these are the things in the data. You can have other things as well if they are predictors or something. Then the next block you have is the parameter block. Okay, so here you define all the parameters of the model. Okay, so even before defining likelihood and prior assumptions, you define the parameters. Why? This is the place where you define what are the parameters and also the boundations or constraints on these parameters. Okay, so for example, first parameter I will define is mu. So real mu, and then real lower equals to 0. So this is a constraint I'm defining, sigma. So sigma parameter with constraint that its lowest value could be 0. The lowest value it can get is basically it cannot go beyond 0, less than 0, right? So I'm defining lower bound on sigma. Okay, so now I defined parameters. Okay, now the final block will be likelihood and prior assumptions. So I think this block is called model, right? So in this block you will write sampling statements, right? How exactly? So one way is this, that you just directly write your sampling statements about prior and likelihood in the way you usually like. So, for example, mu comes from normal 6.1, sigma comes from normal 0.5 with lower bound 0. Okay, so something like this. Then RT comes from log normal mu sigma. Okay. So basically we wrote the prior assumptions and the likelihood assumptions here. So this is how a STAN program looks like, but it is faster and better to write exact, because these statements are misleading. This is not what the HMC sampler is doing. Remember, the MCMC or HMC sampling is not drawing samples from these distributions. It is only using these distributions to calculate densities, prior densities, and the joint likelihoods, right? So what it really does, the algorithm, it does this. Let's say there is a variable target. We are going to store all log likelihood and log prior densities to this variable. Okay, because when we calculate posterior density of a sample, what we do, or let's say when we calculate potential energy of a sample, right, what we do, we calculate its posterior density, log posterior density, right? So log likelihood into prior density, which means log of likelihoods plus log of prior densities, right? So basically it's summation of log likelihood and prior densities. So that's how we write this statement here. So log target plus minus normal LPDF. What it quantifies is the PDF, but on log scale. So log probability density function, that's what it stands for, from a normal distribution. For what parameter? Mu. And given what mu and sigma? 6 and 1. So this is how you can write it. I think I went in other direction. So target, I'm just rewriting the same statement here, plus equals to normal LPDF mu 6.1, then target plus equals to normal LPDF sigma 0.5, and then you also need to subtract something here, which is normal LCCDF sigma 0.5. This is because of the truncation, because truncating this distribution at 0. I'm not going to explain this why we are doing this, but this ensures that you get the right density, because you are assuming a truncated normal prior density here. Then you do the same thing for the likelihood. Target plus equals to log normal LPDF y, not y, RT, right? So that's the outcome vector. RT mu sigma. That's it. So this is your, these are your modeling statements. These are parameters and this is data, right? So when you run this STAN program, it implements HMC sampler in the background. The sampler directly takes these statements because it's really useful to take it in this form, and it does the job for you. Okay. So this is what happens in the background of BRMS function. But our focus would be on this function, so understanding its syntax, and so that you define priors properly, define family assumption properly, basically the likelihood assumption properly, and the other things as well, right? So but the package is actually built for regression modeling. So that's why its syntax looks weird to apply it only for very simple cases, but it makes more sense to apply it to linear regression modeling cases, right? And you cannot apply it beyond that. That's also true. So let me take a quick example of linear model. Of course, we will start it, I guess, in the next lecture, but I can take an example here to understand the VRMS syntax, right? So suppose a participant is seeing some words on a screen, let's say book or dog, but sometimes non-word as well, BKTR, right? Something like this. And their task is to respond with yes and no if the word is a meaningful word in English, and no if it is not a meaningful word in English. Okay. So these are meaningful, for example, this is not meaningful. So here they would respond with a no. Okay. What we are recording is their recognition time. So how much time do it take to recognize these words, right? So recognition times. Okay. Suppose we call a participant for the experiment and we show the participant total 50 strings on a screen, or not 50, let's say we show them total 500 strings on a screen one by one. Okay, we show them total 500 strings. Okay, and we record their recognition time on each string. So how much time do they take to recognize whether it's a word or non-word? So we're recording their recognition times. Okay. Could be anything up to 500 trials, right? Now, if you want to model it using a simple model, so what we can say that recognition time in the ith trial for the ith string comes from a, let's say, a log normal distribution with parameter mu and sigma, where mu comes from normal, let's say 6, 1, and sigma comes from normal 0, 0.5. Okay, this could be a simple model. But suppose, but the problem here is this, that these reaction times, right, which we are assuming reaction time for any ith string comes from the same distribution. So we are making this independent and identically distributed assumption that all these reaction times are independent and they are coming from the same distribution, right? But that's not, that may not be true. Okay, why? What can happen is this, that as you go from trial number 1 to trial number 500, you might get better and better at recognizing these words, right? So what you can observe is something called a practice effect, right? So as you go from trial 1 to 50, you might have a practice effect such that by the time you reach towards towards the end of the experiment, you are getting really fast at recognizing these words. So the recognition times in the beginning are slower compared to recognition times towards the end. So in the end, your recognition times are on average faster. Okay, how do we capture this idea? Okay, how do we model this, or how do we test this, right? First, we need to model this idea. How do we do that? If we make a slight change in this assumption that reaction time for the ith string comes from a log normal distribution mu sigma, but assuming sigma remains the same, but this mu, which is the average, which is basically indicating some sort of average, for log normal distributions is not exactly average, but let us think of it, let's say it's indicating some, no, so for log normal it's indicating some median. So it's a median recognition time. Let's say this median recognition time increases as we go towards later end of the experiment, right? So what we can say that this mu is also dependent on trial ID. So mu is not constant from trial 1 to trial 50, it changes, right? So we assume that RTI comes from log normal mu I sigma. Now assuming mu I is a function of your trial ID, okay, or let's say just trial, where trial can have values 1, 2, 3, 4, 5 up to 500, right? So let's say mu I is a linear function of trial, right? So you can set up a linear function like this, alpha plus beta into trial. Okay? So like this is a equation of a straight line, right? So when trial is 0, so in the beginning the median is alpha, but as trial ID increases, it increases with this rate beta, right? So with each trial it increases by this much amount beta, and by the end of 500 trial this would become alpha plus 500 beta. So that's the idea. So now this whole thing becomes your likelihood assumption. Okay, so now your likelihood assumption is not a single line, it has become these two lines. First, RTI comes from log normal mu I sigma, and then mu I is equals to alpha plus beta into trial ID, or let's say trial ith trial ID. Okay. Now, rather than now, how many parameters do you have? One parameter is of course sigma, another parameter is alpha, another parameter is beta. Alpha is what? Median recognition times at trial 0. Beta is extent with which the median recognition times increases with trial ID. Beta could be 0 as well, doesn't matter, right? So now you have three parameters, alpha, beta and sigma. So you need to define priors for all three. So let's say for alpha you define normal 6.1 prior, for beta you define normal 0, 0.01 prior. Okay, you can have slightly, let's say big, slightly less informative 0, 0.1 as well. Here normal 0, 0.5. These are priors on alpha, beta, sigma. Now you can implement this using BRMs. So now in BRM you will write reaction recognition times are predicted by 1. 1 stands for alpha now, which is the intercept in this case. Okay, 1 plus effect of trial ID. Okay, so 1 plus trial ID. Okay, data equals to df. This should contain now RT as well as trial IDs. Family equals to log normal, and then when you define priors, you define all three priors. Okay, so prior, let's say normal 6.1 on the class intercept. Similarly, prior normal 0, 0.1 on class beta, so basically slope. Okay, so you can call it B, and then prior normal 0, 0.5 on class sigma. This is how you define all three priors. Okay, so this is how you can write a BRMS model for the same. So model will now will give you a posterior distribution for these three parameters. Of course, their name will be different in model output, but will give you estimates for all these three. All right, so this is an introduction to HMC sampling using this BRMS package, and how you can use BRMS package for modeling and for parameter estimation. All right, okay. So I will stop here. In the next lecture, we will see a couple more examples using BRMS, and I will introduce linear modeling as well. All right, thank you.